returning to our discussion on carbon nitrogen bonds or nitrogen containing organic compounds, one very important thing I have not yet talked about is the stereochemistry of the compound. And stereochemistry plays such an important role in the biological activities that one stereoisomer is found to be medicine, the other stereoisomer may be even poison. That sort of biological difference is being observed. Now, if you look about the structure of two compounds where a carbon nitrogen bonds are being shown, this is the alpha bond, here also the alpha bond, the substituents is the beta substituents with a orthochloro thing. This compound, if I put a mirror in between these two isomer, then what I see, the left hand side is the mirror image of the right hand side, and if I take it and fix it on the object, that is the first one, that is not superposing, because carbonyl will be on the left hand side and in this case the carbonyl is on the right hand side. So, the handedness is different. So, this type of compounds which are non superposable mirror image relationship will be called the enantiomer. So, one compound having the S ketamine say plus specific rotation, the other compound is R ketamine having minus specific rotation or vice versa. But one is found to be anesthetic like S ketamine, and look at the biological properties of the other one, that is hallucinogen. So, just by changing the orientation in space, one compound is found to have one type of biological activity, the other compound, the other enantiomer is totally different. So, stereochemistry control, stereochemistry maintaining, and to know that absolute stereochemistry is very important. Not only the compound is whether will be biologically active or not, or if active what type of biological activity it will get. Another important thing sometimes we ask, that all the time people talk about the chirality where carbon is being present, as if carbon other than carbon the chirality can not be there. It is not correct. But again some compounds we find where the chirality is coming from other atoms, say nitrogen chirality center. If I take a compound where nitrogen having the lone pair of electron tetrahedral, the fourth is the lone pair of electron staying, and three substituents being shown here as a cartoon, pink, red and green. And if the other enantiomer being written, again this is the mirror image of that, non superposable. So, these two are enantiomer. But if we look at the nature of this compound, we do not see any sort of enantiomers getting separated out. That is called amine inversion. What is that? How can one amine could be converted to the other amine? Very clearly being written, this structure is sp3 hybridized, the tetrahedral 3 groups are there, R1, R2, R3 regular tetrahedron, and the fourth substituent is the lone pair of electron. So, this is getting converted in the transition state to an sp2 hybridized carbon. So, sp3 to sp2 where the p orbital keeping the electron pair, and then it is reverting back, either coming back to the starting material or to the other form where the nitrogen lone pair is below the plane. So, what is happening? This is the inversion is taking place. So, amine inversion, is it very slow or very fast? Very common knowledge says the inversion barrier is only 6 kilocalorie per mole for our alkyl group, that is R1, R2, R3. If there be alkyl, they can be converted from one enantiomer to another enantiomer just by putting a simple little energy at 6 kilocalories. So, they are in rapid equilibrium. So, what is the problem? Problem is you cannot catch one of this enantiomer from this rapid equilibrium thing. Whenever you want to get one, it is getting converted to other. So, overall thing will be two enantiomers not being separable, or resultant thing is racemic. So, how to convert that? This is the inversion barrier is very low. Another very nice data is ammonia inverts 2 into 10 to the power 11 times per second, unbelievable. So, you cannot get that ammonia, substituted ammonia in the chiral form, because whenever you are going to catch one, it is getting converted to the sp2 and then to the other form. And so, that is so rapid equilibrium, it is very difficult unless very low temperature and the energy barrier is being imposed, then and only then you can do. But there are tricks for other organic molecule having carbon nitrogen that you can do it. That is, inversion becomes slow when nitrogen is in a strained ring, that is 3-membered ring. In that case, like ammonia or substituted ammonia, that inversion will not be fast, but it will be slower. Why? Because 3-membered rings, mostly 60-degree angle, that bias strain as per bias strain theory will be very strenuous. So, to convert it to the sp2 hybridized form, that because from sp3 cannot straight away go to other sp3, it will have to pass through that sp2 form, sp3 to sp2, then another sp3 I mean. So, these enantiomers of 1,2-dimethyl aziridine, aziridines are those compound where one carbon nitrogen bond is present and 3-membered ring, instead of carbon one nitrogen is there, the nitrogen is methyl substituted, carbon is also methyl substituted, another is a free carbon, that is having 2 hydrogen atom. So, this type of enantiomer of 1,2-dimethyl aziridine, aziridines are 3-membered nitrogen containing compound, nitrogen is numbered as 1. So, N-methyl, 1 position 1 methyl and 2 position the next one is the another methyl. So, enantiomers of 1,2-dimethyl aziridine is very much being obtained. So, one way to solve this problem is making some bridge or making a small ring, so that the inversion barrier is being imposed, and that is why one of the enantiomer could be separated. So, that is the trick to get a chiral nitrogen compound. So, of course, the answer I have already given, nitrogen cannot achieve a 120-degree bond angle, as it is in a 3-membered ring, 60-degree dihedral angle, it will be very difficult, and so it will be remaining in the chiral form. The two enantiomer can be separated. So, that is a very nice trick to get the chiral nitrogen compound. Nitrogen atom is connected to atom which are unshared lone pair of electron, like this. If I put this picture in this way, then what is happening? A 3-membered ring with nitrogen, that is a chlorine substitute, and in this structure also this methyl, this is the thing, this is not the chiral center because symmetry is there, that is methyl, this is also methyl. But this is the chiral center where nitrogen having chlorine, having cis Me, and another is the lone pair of electron, and another fourth group is CH2. So, all 4 different groups are there, the fourth one is the lone pair of electron. So, this is the mirror image of that, and this mirror image is not superposable on that. So, this is a also 2 pairs of enantiomer which could be obtained, which could be separated and which could be used for purposes. So, one trick is making small ring, then the nitrogen inversion could be stopped. But if it is acyclic ammonia derivative, very difficult, because the interconversion is very fast. One more example is here, that is Stroger's base, where a benzene ring with carbon nitrogen carbon is there, it is symmetrical 2 benzene rings, and there is a bridge between 2 nitrogen atom through a methylene group. This type of bridge ring structure are very important. So, Stroger's base also could be obtained in a chiral form, because here the flipping will not be possible, or in other way the interconversion of the normal to the pyramidal nitrogen will not be possible because of the strain in the molecule or bridge in the molecule, which the conversion of sp3 to sp2 will be stopped. Another very interesting feature, look this thing very carefully. If we have a XY bond, sometimes X is keeping the negative charge and another resonating form, it is coming over here and the one of the bond getting localized or polarized to the Y group. So, negative charge is shifting from X to Y or Y to X. What do we call this type of phenomena? Double headed arrow means resonance. So, these are two resonating structure. In one case X is the nucleophile, in other case Y is the nucleophile. It will be very clear if you look at this in this box, there are two compounds are there. One is our preferred one, that is nitrile C triple bond N, where carbon is the negative charge, that is the nucleophile, or C double bond N minus, that is another pair of electron is with this carbon. So, that is the nitrogen is the negative charge. So, when a species having a negative charge not localized, but delocalized, sometimes with X atom, sometimes with the Y atom. So, it can bite as if with several teeths are there to the substrate which is positively charged, that is C plus. That sort of phenomena or that sort of nucleophiles are called ambident nucleophile. Ambident nucleophiles, we know nucleophiles negatively charged or non-bonded electron pair which can donate to the substrate. Nucleophiles which have more than one, generally two or more suitable atoms through which they can attack the substrate. They are attacking the substrate means they are attacking the positive end of the substrate. So, negative end should attack to the positive end, and how that thing will take place and who will control that, whether X will attack or the Y will attack, and what we call that type of species X Y delocalized, we call it ambident nucleophile. And I will show you a very nice example where we can control the attack either by carbon or by nitrogen by changing the environment or putting some catalyst. Look at this. RBr treated with silver cyanide. This is very much carbon nitrogen bond related problem. Alkyl bromide treated with silver cyanide, you get a slow process. Any alkyl bromide, methyl bromide, ethyl bromide, etc., treated with silver cyanide AgCN. What will form? It will form silver bromide which precipitates out. We know the silver nitrate is a good reagent, that sort of thing will take place. Silver nitrate, silver is monovalent, and at the same time the RBr will get polarized to R plus and Cn minus. Fine. And this reaction follows very fast pathway to get RNC. Look at this. Cn minus is being written in the third bracket, but the product being shown that it is Rn plus and C minus. That means, the R plus getting attacked by the Cn through the nitrogen, not to the carbon. That means, nitrogen is the attacking species, whereas just simple change. The same alkyl bromide when treated with sodium cyanide NaCN, what we see? We get RCN. So, this type of thing is called nitrile, this type of thing is called isonitrile. So, totally two different type of mechanism is taking place in this case. When we are using silver cyanide, we are getting one type of product which follows substitution nucleophilic unimolecular reaction, which is being written here very clearly as SN1 type, and in the second case it undergoes a, we have discussed about the substitution nucleophilic bimolecular reaction, that is a transition state, no intermediate gets involved. So, it gets R, Br and Cn coming in this fashion. So, C is the, because whenever cyanide is being produced, C is the negative end and that carbon attacks to this R and you get RCN. So, there is no question of any isomerization or any stepwise process here, it is a transition state mediated process. We know a reaction which goes through transition step only is SN2 type, a reaction which goes through an intermediate, that means first transition state, then intermediate, then second transition state, then to the product, we call it an SN1 type. So, why silver is doing that, sodium cannot? Answer is, silver plus promotes the formation of R plus by the formation of AgX, because that rate of reaction is very fast. Silver reacts with X very quickly and that generates the R plus, whereas sodium cannot do that. So, nucleophile attacks from the side in which it has more electronegative atom, very clear answer. What is that? the nucleophile is Cn, whether C minus or N minus, that we will have to know. Answer is, as silver promotes the formation of R plus by the formation of silver halide, Ag is being formed, X has been taken care of. So, R plus is there. Nucleophile attack from the side in which it has more electronegative atom. Out of carbon and nitrogen, which one is more electronegative? Nitrogen. So, obviously, it is not getting any chance to rearrange. So, you get RNC is the product. Think very carefully. Silver plus promotes the formation of R very first by the formation of silver halide, generating the nucleophile to attack normally. What is that? The more electronegative side should attack first. More electronegative out of carbon and nitrogen is nitrogen. So, nucleophile attacks from the side in which it has more electronegative atom. So, you get RNC by SN1 mechanism, whereas sodium plus does not show such promotion for the formation of R plus, because compared to silver, sodium plus is very normal, it does not take part the precipitation that rapidly. So, what it does a normal SN2 type reaction, that is a transition state where carbon, because in cyanide Na plus Cn minus, the negative charge is on carbon now. So, carbon gets directly attached to R through the transition state like this, and you get RCN. So, very nice take. One, you can get RCN. If you want to get RCN, follow sodium cyanide. If you want to get RNC, follow silver salt. This has been used in number of other cases like RBr silver nitrite, AgNO2, slow process, silver bromide, then fast process RONO, very nice, that is NO2 acting as RONO. We took NO2 plus yesterday and we found that NO2 could be reacted in ONO. So, NO2 minus is a case where it is an ambident nucleophile. It might attack through nitrogen, it might attack through oxygen. When it is an SN1 case, more electronegative atom is attacking, the same phenomena, same logic. When it is a RBr sodium nitrite or potassium nitrite KNO2 case, then we get a transition state and the product is being obtained as Rn, not RO. RONO, this is RNO2, totally different compound by changing the inorganic component from silver to sodium. One is following SN1 mechanism, another is giving SN2 type mechanism. So, this is a very nice role of ambident nucleophile. Okay. I said about carbon nitrogen single bond, carbon nitrogen double bond, and very nice case of an ambident nucleophile as carbon nitrogen selectively carbon could be attacked to the substrate that R, or nitrogen could be attacked to the substrate R. Now, another type of thing very much helpful, because how you can convert now amide to amine by Hofmann degradation reaction, amine to amide, that I told you. If you want to make some amine from nitrile RC triple bond N, how can you do that? Basically, nitrile is this and amine is RCH2NH2. What is difference here? This triple bond has been removed to single bond and 2 hydrogen being added to each carbon and the nitrogen atom. That means, 2 hydrogen being added to the triple bond to convert that C triple bond N to CH2NH2, that is primary amine or 1 degree amine. So, that process will be called hydrogen addition or reduction. So, reduction of any of these functional groups by catalytic hydrogenation, or another very good reagent is lithium aluminum hydride, mixed hydride, lithium hydride and aluminum hydride AlH3 and LiH together LiAlH4, that yields an amine this way. If you take an oxime, oximes are double bonded N, OH group is there, oxamine. So, it is called oxime. When you reduce that thing, you end up with RCHNH2. That means, oximes are often reduced with sodium metal in alcohol, that is another reducing agent system, sodium alcohol, potassium alcohol, that is also being used. So, to make the amine, not necessarily you will have to do simple SN2 type reaction. You can start from a triple bonded thing, follow stepwise reduction, or one step both the bonds getting reduced. So, one way is by hydrogen or lithium aluminum hydride, another way starting from nitrile or oxime you can make primary amine, or in this case very nice example RCO in R prime double prime amide, you can get primary, secondary or tertiary amine very nicely as per your desire, as per the substituent. So, another trick or another technique to get the amine from the nitrile is by reduction, and reducing agents are hydrogen generated in situ or lithium aluminum hydride. Sometimes other hydrides could also be used. I said about antibiotics and the discovery of penicillin. One of the very simple molecule where carbon nitrogen bond is no doubt present, but again a sulfonyl group is also present. These compounds are also found to have antibacterial property. That was the first discovery of the antibacterial properties of certain compound. In 1936, from the Louis Pasteur Institute in Paris, a sulfanilamide, look at this terminology, sulfanilamide, sulfonyl means SO2, amide is NH2, and in this case there is another amine group in the 4th position. Sulfanilamide was found to be the first sulfur drug. There are many use of sulfur drug, not only antibacterial activity, but other thing. In the following years, many thousands of structural variation of sulfanilamide were synthesized in the search of additional drugs. So, this is also a very nice breakthrough in the case of sulfanilamide or sulfonamide thing discovery. Protoalkaloids, I said about some of the alkaloids. Another very important alkaloid is mescaline, ephedrine, that is being used for treatment of cold. Condition caffeine, caffeine is almost every day we use in tea or coffee. That has a very nice structure. You can say that right handed the 6-member ring is pyridine type, but in the 3 position there is another nitrogen atom. Likewise, the right hand type is a pyrrole. So, it is a pyrrole pyridine combined, but again in the 3 position there is another nitrogen. So, one pyrrole moiety, another pyridine moiety, somewhat different oxidation state. This side is the 2 carbonyl groups. This is nothing but caffeine. Caffeine is obtained from tea dust, caffeine is found in coffee and many other things, and it has painkiller activities, it has medicinal activities of other type, and to certain extent it is addictive also. So, connichine is another alkaloids. I have some more structure where the alkaloids have been classified depending on the structural features present. Like if I ask what type of alkaloid is this one, answer should be pyridine, because pyridine is this, when reduced form is pyridine. What type of structure is this? That is pyrrolidine. Tropane is another nice compound. One example I gave you. Quinoline is a benzopyridine. Isoquinoline, the nitrogen position is different in quinoline. It was 1, now it is in 2 position. Tetrahydroisoquinoline means one ring is fully reduced, that means saturated. Indole, that the thing I told you already, indole with another indole making indigo with some substituent of the carbonyl group, that is nothing but benzopyrrole. That means a benzene ring and a pyrrole ring, that is the 5-member rings are there. Imidazoles are the building blocks of the proteins or amino acids, many compounds. That is 1 and 3 position, there are 2 nitrogen atom, it is a 5-member ring, that is imidazole. And purines is 1 and 3 position exactly like this, that is pyrimidine type thing, and 1, 1, 3, that is imidazole type thing. So, pyrimidine, imidazole together is giving a very important class of compounds. In the building blocks of life, many material is purine. So, all these are nothing but carbon compounds having nitrogen or carbon nitrogen bonds are there. Okay, these are some of the natural sources where from you can get the alkaloids. Some pictures are being shown just to get the how the coca leaves or other things. Yeah, I did not say about another very simple compound. Look at this, this is a pyridine being attached to a pyrrole, very simple, nothing else. But pyrrole is somewhat reduced. By reduction of the pyrrole moiety, what we have got? We have got a new chiral center, which was not there. If it is pyrrole, there is no chiral center, the compound is not chiral. But when you reduce it and you get a chiral center and you exclusively that be the hydrogen beta, then one type of enantiomer, if hydrogen alpha, that will be another type of enantiomer. So, nicotine is also being present in all those beverages, and many narcotics activity is also there, and nicotine is very good as a stimulant also. These are nothing but again some example of carbon nitrogen compound, that is nitrogen containing organic compounds. Arycholine in methyl, but there is a substitution in the 3 position with COOCH3. Sometimes one thing should come to your mind, and most of the examples what we are taking, that is pyridine in the 3 position there is a substituent. Why not in the 2 or 4 position? Answer is very simple. Biologically, or the biosynthetic pathway by which these compounds are being produced, they follow the pyridine 3 carboxylic acid path. That means, nature is producing exactly in that fashion. That is why mostly 3 substituted case in case of pyridine or substituted pyridine are the natural products. But people can synthesize in other position, as in this case. This is the 2 position substituted pyridine, that is called Loblin. Loblin could also be prepared by the similar method. Okay. Now, I will show you some of the interesting reactions of the carbon nitrogen bond. Let us take this example. If you have an CH3 CH2 NH2, let us take this compound as a 1 degree amine. One thing is there, the next to the nitrogen, the first carbon is called the alpha carbon, the second carbon is called the beta carbon. So, this is a 1 degree amine, because CNH2, that NH2 is free, and there is a beta hydrogen being present in this molecule. So, if you treat with excess of methyl iodide, what will be the product? Think. You have a beta hydrogen substituted ethylamine, treating with excess of methyl iodide. So, what methyl iodide will do? Will pick up the lone pair of electron from nitrogen and break the carbon iodine bond. So, as a result you get NCH3, one hydrogen getting expelled out with the help of iodide. And then in that way, if you do the further methylation, you end up with trimethyl alkyl ammonium iodide. That means the quaternary salt N plus and I minus. Now, one very nice discovery was done by Hofmann. What is that? If this type of compound where a quaternary nitrogen is there, counter ion may be halide, that is Br minus or iodide minus, treated with silver oxide in presence of water, you get the trimethyl alkyl ammonium hydroxide. Fine. Now, this compound when heated, then what will happen? We mentioned that there is a beta hydrogen present in this compound. Then it is found that it is heated with mild base or little bit of water that picks up this proton, that is beta hydrogen, and the electron pair forming bond between carbon and hydrogen shifts towards the next carbon. As a result, the nitrogen which was positively charged have been thrown out of the system. So, what you get? You get an alkene. This type of reaction is known as Hofmann elimination reaction. What is elimination reaction? When two groups leave the system at a time, their relation may be alpha, may be beta, may be gamma or delta or omega. That type of reactions will be called elimination reaction. What is the driving force here? The hydrogen getting picked up by the base and the N plus with 3 bulky groups or methyl groups is the quaternary salt. So, that bond will be much more labile or very easy to break. So, that is one leaving group and hydrogen is the other leaving group. As a process you are getting with the alkene. This is an example of Hofmann elimination reaction. Cyclohexyl methyl trimethyl ammonium hydroxide, if you take this example and do an OH minus, what will happen? Again with respect to this N plus, this is the alpha carbon, this is the beta carbon, you can take this side also, no problem. You get the this will be the gamma, but when beta hydrogen is present, then that will be the preferred one. So, what it will do? It will shift over here and break that carbon nitrogen bond, that will be eliminated as trimethyl amine and you get the C6H5 double bond CH2. I think you have seen this type of reaction where an alkene is being produced and then in the difference here compared to the other things what you have seen, that you get the alkene mostly in the more substituted position, but in this case you are getting the alkene in the less substituted position. Why this difference? This type of products are called Hofmann product and the where more substituted alkene is being produced is called the Regiochemistry product. And for Hofmann product, the N-alkyl or quaternary salt of N-alkyl is very important, that is why you have picked up this example over here. So, this is a nice way to make the alkene in a less substituted site. So, this is a Hofmann reaction or Hofmann product. Now, in quaternary ammonium hydroxide that have two or more non-equivalent beta hydrogen, look at this, what do you mean by non-equivalent beta hydrogen? Say this example, there is a beta hydrogen over here, there is another beta hydrogen in this side. So, what will be the product? How you will be able to identify the product? Rule is, in quaternary ammonium hydroxide that have two or more non-equivalent beta hydrogen, non-equivalent beta hydrogen means this is alpha, this is beta, this is alpha, this is also beta. So, this is one type hydrogen, this is another type hydrogen. So far the example I took earlier, there was only one beta hydrogen as in this case. Yeah, here there is only one beta hydrogen. So, there was straightforward, no ambiguity was there, but when there are two beta hydrogen, then which one will be the major product? You will have to analyze it and to find out an answer. The major product results from abstraction of the more or most acidic beta hydrogen. Acidic protons will be very easy to lose because acid is a proton donor. So, which proton is more acidic, that will be easy to leave the system. If there be two beta hydrogen as in this case, which one is more acidic, that will leave, the other one will not leave, or if it leaves it will be less in amount. In this case it is very clear that CH3, that hydrogen, what is happening is more acidic, whereas this more substituted CH3 is less acidic. How did I say that? Answer is very simple, because these two methyl group donating electron to the carbon. So, electron density of this carbon is getting increased, whereas here only 3 hydrogens are there, no methyl groups are there, only one push is from other side, that is they are common to that. So, obviously, the electron density on this carbon will be more than this one, and when the electron density is more, then obviously, the hydrogen will be less acidic. So, more acidic hydrogen will be the less substituted one, and you get the major product as this one. That is why Hofmann product, the regiochemistry, regio means region, which region the double bond will come, in the terminal one, less substituted one, or the more substituted one, that is either Regiochemistry product or the Hofmann product. In Hofmann product again, if there be 2 beta hydrogen, which one will be selectively eliminated in the elimination reaction? Answer is which one is more acidic, because more acidic will be easy to leave. How to know which one is more acidic? What sort of other functional group or electron donating or electron withdrawing group is present, that you will have to calculate and check, and steric factor also comes in the rescue, and it says that this is more acidic. So, you get major product as this one. I will tell about another interesting feature, right. You know one very nice elimination reaction, when an alkyl halide, say ethyl bromide, being treated with alcoholic alkali, ethanolic KOH, what is the product? You get an elimination reaction. If you treat that same alkyl halide with strong alkali, what you get? The corresponding alcohol, that is an SN2 type reaction. So, in a beta elimination reaction, that is, if we take an N oxide, what is that? N oxide, look at this transparency. Essentially, a variation of the Hofmann elimination, the cope starts with a tertiary amine oxide. What is a tertiary amine? That is all three, 2 hydrogen and the substituents are there, there is no free hydrogen, and when this is being oxidized, the lone pair of electron of the nitrogen has picked up that O minus. So, it is the N plus O minus. So, this type of compounds are called N oxide, a tertiary N oxide. Why tertiary? Because this nitrogen, all the substituents are there, no free hydrogen. What it does, because of the proximity next to this carbon, that is alpha, beta, this carbon having a hydrogen atom, O minus will pick up this hydrogen, the carbon hydrogen bond shifts over here and the carbon nitrogen bond breaks. So, I can say it is a Hofmann type reaction, Hofmann type elimination, but extra thing is O minus is picking up that hydrogen, that acidic hydrogen, and making a almost a cyclic transition state to give a product which is nothing but an alkene and an dialkyl hydroxylamine. This type of reaction was studied by Cope. From his name, it is known as Cope reaction. One new terminology you can see here, scene elimination. What does mean by scene elimination? The hydrogen and nitrogen, whatever the groups are, they are leaving the system from the same side, that is the SYN. Scene means from the same side, Cs. Or if they leave from the opposite side, one very important thing is the two groups what it leaves are anti to each other. If it is a cyclic compound, it is very anti means opposite, and opposite of anti is syn. Syn means the same side the two groups are leaving. So, that is why the terminology syn is being written over here. So, another example is shown, that is cyclohexyl methyl dimethyl amine oxide, 2 methyl oxide. O minus will pick up the same way the beta hydrogen, and the carbon hydrogen bond electron pair shifts over here, the carbon nitrogen bond breaks, and you get almost exclusively 98% of methylene cyclohexane. So, these are the advantage of the carbon nitrogen bond formation or carbon hydrogen bond breaking to make new compounds over there. I will now take you to some of other interesting case of the carbon nitrogen chemistry. Let us start with a compound where we have a structure like this. Look at this structure, benzene with another benzene means naphthalene. In the one position there is an oxygen, if that be oxygen with hydrogen, that is called alpha naphthol. But other than that, there is a CH2, CHOH, CH2, NH, CH, CH3, CH3, a long carbon chain ending with a isopropyl group. So, this compound is found to have a heart stimulant, or it is a very good heart stimulator, very simple compound. If I ask you how one can prepare this compound, because it is a carbon nitrogen compound or nitrogen containing organic compound, how to prepare? Answer is, when you are adding, look this part, whenever you want to find some way out, it is better to break the molecule in such a way, so that you can make it very easily. And what you see, this portion is CH3, CH, CH3, NH2, NH being replaced by NH2. So, CH3CH, CH3NH2 being treated with some compound, and I should say NH2 is the negative end. So, the some other compound, that means some other site where the carbon will be the positively charged. This concept making carbon positive, nitrogen negative is from the knowledge, from the experience, and this is dependent on the latent polarity. And as I told the other day, the terminology is for the Syntone. These are the Syntone, carbocation or nitrogen anion, these are the Syntone. So, if that be the Syntone, what is the synthetic equivalent? What is the starting material? Answer is simple, epoxide is the starting material. This is a very stable compound, and another answer is CH3CH, CH3NH2 is the second component. So, this is starting material number 1, this is starting material number 2. If we treat them together, they should undergo exclusively one type of thing. You know, this type of compound is called epoxide, ethylene oxide, epoxide. So, epoxide when treated with a nucleophile, where it can attack? It can attack over here and open up this carbon oxygen bond, or it can do the other way around, means it can attack to this carbon and break this carbon oxygen bond. Which way it will take place? The solid arrow it will take place, the broken arrow it will not take place. How did I know? Very simple answer. Whenever this type of reaction is nothing but a SN2 type reaction, whenever a nucleophile attacks a substrate, and if it is an SN2 type reaction, the leaving group and the nucleophile should be in one line or 180 degree approach angle. This is number 1. That could happen over here also, this side also. But during that process, you get a transition state where almost carbon is pentavalent, means very much crowded. So, what the nucleophile will prefer for an SN2 type reaction? A less substituted carbon. And if you look very carefully, this is CH, CH2 and this is only CH2. That means, here there are 2 hydrogen, here there is only 1 hydrogen. So, that is the reason the less substituted side will be attacked, less substituted side will be attacked, then you end up with this compound. Then question come, how come such a big molecule you can prepare? Answer is not big. If you break it again, you end up with OCH2 CH double bond CH2 from this. How did I write? Again cutting the epoxide in this way, taking off the oxygen. Then if I ask you, how can you convert a CH double bond CH2 to an epoxide? Your answer will be, I have to get an oxygen which is positive, O plus, because CH double bond CH2 attacks an O plus oxygen which is positively charged. What is the source for oxygen positively charged? That is the reagent. It may be hydrogen peroxide, as simple as that, peroxy linkage is there, or it may be one very nice reagent is par acid. Par acid means a carboxylic acid is COOH, a par acid peroxy linkage is OO linkage will be there, COOOH. In this case, the 2 oxygen are not equivalent. Why? Because one oxygen being attached to carbonyl, another oxygen being attached to hydrogen. So, this type of peroxy linkage is needed for the oxidation of an alkene to the epoxide, and it is the O plus which gets picked up, and obvious reason will be this oxygen will be picked up and this COOO will be converted to the COO minus, and you end up with the corresponding epoxide. So, this is a very general rule. That type of phenomena, why selectively one oxygen of the hydrogen peroxide or metachloroperbenzoic acid or perbenzoic acid or paracetic acid gets picked up? The answer is, this is the alpha effect nucleophile. What is that terminology? if two heteroatom, in this case oxygen may be with sulfur or nitrogen or other thing, being linked together, the electron pair forming bond between them are not equally shared. The one which gets the lion's share is the nucleophile, and one which leaves its share is the electrophile. That electrophilic oxygen will be picked up by the electron rich alkene to make it epoxide. Okay, you can look at this and say that this is also very awkward looking molecule, how to prepare that? Not much difficulty. As I told you, you should break it in such a way so that you can make it very easily. I did not break it over there, I just broke it over there. The idea is the two component in this case will be a naphthalene derivative with a O minus over here and a CH2 CH double bond CH2 with a plus on that side. Why I did not put oxygen plus or carbon minus? The answer is oxygen is more electronegative. So, negative charge will be more stable and carbon is more electropositive. So, put the positive charge on the carbon. So, what is the, these are the Syntone. What is the synthetic equivalent? O minus K plus you can put it, and the corresponding ion you can put the bromide ion. This is nothing but allyl bromide, very standard compound, commercially available. So, when allyl bromide is treated with alpha naphthol, the reaction is very simple. O minus will attack this carbon, throw away the bromine, and you get O CH2 CH double bond CH2, not at all difficult. So, a simple trick can help to get a complicated structure to be synthesized very easily by this pathway. And I will tell you one more interesting feature over here, that is, if I write a structure like this, a benzene ring with a carbonyl in H with another carbonyl, and ask you what sort of compound is this one? We have seen this type of compound, that is benzene ring with two carboxylic acid groups side by side, that is 1,2 dicarboxy benzene, dicarboxylic benzene. When that is being heated, it forms an anhydride, and the anhydride being treated with ammonia, you get that type of imine. So, that is called, this is again carbon nitrogen bonds are there, that is called phthalimide, PHTHALIMIDE, phthalimide. Phthalimide is very interesting compound in that sense, the Gabriel's phthalimide synthesis that you have studied in textbook. So, it could be this hydrogen is very much acidic, with the help of a base or mild base even you can generate the N minus, and this N minus can react with many compounds. Say one example I right now showed, say allyl bromide, it could attack over here and can be connected to that group N CH2 CH double bond CH2. So, many compounds in that way could be prepared by using the phthalimide. What is the advantage? The advantage is this hydrogen is acidic. Why? Because if you take off this hydrogen, the remaining thing, that is the conjugate base, is nothing but this N minus plus H plus. One very general rule is which one is stronger acid, sometimes you have to answer, say benzoic acid and phenol. After the loss of proton from phenol, we get the phenoxide ion, we can write 3-4 resonating structure, whereas for benzoic acid, after the loss of the proton, the benzoate anion, we can write 2 symmetrical resonating structure. That is very important. The contribution of symmetrical resonating structures towards resonance hybrid is maximum, and because of that the proton loss will be much easier when the stability of the conjugate base is more. So, that is the reason why benzoic acid is stronger than phenol. Likewise, this compound will be also stronger acid, the reason being it can have a symmetrical resonating structure where the electrons are getting delocalized on both sides, on this carbonyl, another to that carbonyl. Now, if I at this stage, if I ask you another very simple question, and of course, I will give you the answer. Instead of this, if I write a structure SOO, that is sulfonyl being attached to NH, can you guess the acidity of this proton or strength of this compound so far as acid strength is concerned? It is unbelievable, because this proton is lost so easily. Why? Because after losing the proton, the remaining portion, that is SO2 this side, SO2 that side, the nitrogen atom having the lone pair of electron gets delocalized in number of symmetrical resonating structure. More the symmetry, more the stability, more symmetric resonating structure of anions. How this anion is being produced? By the loss of the proton, that is the conjugate base. Conjugate base. If a conjugate base is very stable, obviously the loss of proton will be facile, and it will be unbelievable. This compound is found to have an acid strength of 12 normal, like concentrated hydrochloric acid. And this type of carbon nitrogen system have been utilized, because sulfonyl, sulfur having d orbital, it can hold the electron for longer time, it can delocalize and it gets stabilized by, in the previous case you have 2 carbonyl, now in this case you have SO4, S double bond O bond. So, that is why more symmetrical structure, more time to spend the electrons over there, and more the stability of the conjugate base means stronger acid. And one important thing is, what is the most electronegative element known? Your answer will be fluorine. And if by any way we can make this type of compound, very simple one, this is doable and people have made it, SO2 SO2 and F. We can take this fluorine being attached at this stage is not electronegative, it is almost electropositive. I will tell you how. If I bring some species like O minus Li plus, that is called enolate, what happens? This picks up that fluorine and breaks the fluorine nitrogen bond. Exactly the way it picked up the hydrogen, it can pick up this fluorine, and the remaining thing is SO2 N minus, because this is very stable, and as a process we are getting the CO and F, fluorine being attached. So, this type of reaction is called electrophilic, unbelievable, electrophilic fluorinating agent or electrophilic fluorination. So, electrophilic fluorination is a very offshoot or very interesting feature which is coming from the 2 carbonyl thing being extended to 2 sulfonyl pathway. So, this is the acid strength over there. Okay, I will give you some problems what you can do. If you are not able to do, next time I will give you the answer. Predict the product. Number 1, if aniline is the substrate treated with bromine and water, what product will you get. Second problem, if phthalimide, right now I wrote that one, CON minus K plus is the substrate being treated with benzyl bromide C6H5CH2Br, what will be the product, and that product is treated with KOH and water heat, what will be the next product. Third problem, if I take a ketone COCH3 and treat with ammonia NH3 in presence of followed by hydrogen and nickel and under pressure and heat it, what will be the product. And the last one I should say is C triple bond N having this being treated with hydrogen, nickel and heat, what will be the product. All these things I have discussed during this 2-3 hours lecture, now 4 hours. You should be able to answer. If not, I will give you the answer in the next lecture. Thank you very much and enjoy.